Good afternoon, everyone. I'm Andrew Marsh, Program Officer for Leigh Ann Conn Prize for Renewable Energy. We'd like to thank you all for taking the time to be here today to hear a public lecture by Dr. Shuji Nakamura. Dr. Nakamura is our 2019 Prize Laureate, and we had to delay his visit somewhat because of this nasty little pandemic that we've been enduring. So thank you all for your patience and for being here today. Shuji is an electronics engineer and an expert in materials development. He's a professor at University of California, Santa Barbara, and credited with the invention and optimization of the blue LED, which makes white LED lighting possible. So if you would please put your hands together for Shuji Nakamura.
Thank you. Thank you so much for inviting me here. And also, it's a great honor to receive the Leigh Conn Prize this time. Thank you. So today, I'd like to talk about how I could invent the blue LED, also the future solid lighting in the future, LED also laser diode. So at first I introduce myself. So this is Japan. So Japan is composed of 4 islands. And the smallest island is called Shikoku Island. It's located south of Osaka. And so basically I was born here, I studied here, and I worked here. Then after invention of LEDs, I left Japan to the United States to become a professor of UCSB. So, so basically, I was born here. It's a small fishery village. I think maybe this one, me. And at the second grade elementary school, I moved to the Ozu city. This is a little big city in Japan, but it's a small still. So I enjoy the volleyball. So this is me. So up to from junior high school, and I enjoy the volleyball. So that's the reason my grade was not so good. So I could barely enter the local university of Tokushima University. It's a very small university, local university. In Japan, big university means big city name, Tokyo University, Osaka University. It's a Tokushima University. So it's a small university, so only up to master degree is available, no PhD course. So after getting a PhD degree, I graduated and I joined the small chemical company located in Annan City. It's a small chemical company, name is Nichiya Chemical Industry. When I joined this company, number of employees was about 120. Annual sales is, I think, $20 million. So I worked with this small chemical company for 20 years. So first 10 years, I developed 3 products, but sales was very poor. And then remaining 10 years, I could invent the blue LED, green LEDs, white LEDs, also blue laser diode. So this is a chemical company, no semiconductor technology background, 0. So, and also problem is company founder didn't like any collaboration outside of the university and industry companies. So we developed everything ourselves, independent from outside. It's a local small company, chemical company. So it's an amazing story, no? No background, 0. We had to develop everything. Also money, funding is small, tiny funding. So basically, all of equipment, everything homemade, basically, to save money. So it's amazing story. So, and this is my first day at the company. This is me, and this is the company's founder, Nobuga. I respect him. I worked for this company for 20 years. Only he could support me for 20 years. First 10 years, sales was very poor. I developed 3 products. These other big bosses complain a lot. You have to take a risk, you have to quit the company. But only one person, top guy, could support me for 20 years. That's the reason I could invent blue LEDs, because without him, I couldn't invent blue LEDs. Okay, so incandescent is a small chemical company, no? So this shows the efficiency of the red and blue-green LEDs as a function of the basically developed years. So basically, red LED was developed in 60s, and the efficiency of red LED increased gradually like this. But in order to make many kind of colors, we need 3 primary color LEDs. So it means that we needed the blue and the green LED. So since 60s, all over the world, many scientists tried to develop blue and green LED, but nobody could make it. They spent a lot of money and a lot of great science work, nobody. But in 93, suddenly, in Japan, local chemical company announced the mass production of blue LEDs. Nobody believed it, because suddenly, mass production, making a product. So we put the demonstration of blue LEDs at the Tokyo and Osaka office. So all, many scientists came to this Tokyo and Osaka from all over the world. And then they was, oh my gosh, this is true, no? So that's in 93, Also, we developed the green LEDs in 95. So basically, since 95, 3 primary color LEDs available. So basically now, since 95, we can make white LEDs also the display. But this white is a special one, just also we developed white LEDs just using blue LED and phosphor. By combination of phosphor and blue LED, we can make white LEDs. Basically, phosphor changes the blue color to white. So now, white LEDs efficiency is about 200, 300 lumen per watt. So I mean that this efficiency is almost, how many? 3 times or 4 times higher than the fluorescent lamp. Also, I don't know, 10 times or 10 times higher than the incandescent lamp. So now, using a white LED lighting, we can, save a lot of energy. So in my case, my story is 79. Here, I joined the nuclear chemical industry after graduation from local university. So first 10 years, basically, I had to develop these conventional red and infrared LEDs. And I could develop 3 products. But monthly sales only $10,000, so no profit. And then I told them many companies, bosses started to complain a lot. You have to quit the company. So in 1988, I'm so desperate to improve my research style and research subject. So despite I went to the small companies, I went to the chairman's office. Can I do blue LED research? He said, okay. So also I had never used a big funding. It's a small company. So I despite asking him $5 million to the blue LED research. He said, okay, no problem. And next, I never been to foreign country, so can I go abroad for 1 year, especially to United States? He said, okay, no problem. So everything okay. So it's amazing. So why blue LED means that just when I started conventional red LEDs after joining a company, I did a lot of scientific papers and patents. And all scientific papers say biggest problem of LED is no blue, no green LEDs. Even somebody invented the blue and green LEDs, they are the huge market. So I wanted to do the blue LED research just after joining a company. But when I talked with my boss, my boss R&D group boss always said, oh, Nakamura, you know my company, our company has a research funding? No, 0. And the next, you have a knowledge of the semiconductor? No, I have nothing. So no way, because during those periods, for example, in Japan, like Sony, Toshiba, Panasonic, NEC, all of it, big semiconductor companies spending $100 million to develop blue LEDs for 3 years. 3 years, they are spending $1 million. Like United States, Hewlett-Packard, in Europe, Siemens, now Osram. Those companies spend a lot of money. Also, they formed a project team. Project team is composed of 5 or 10 scientists. they had a PhD degree, no? And so in my case, only alone, and no background semiconductor technology, zero. So no way, I gave up. But 88, I became desperate. So I asked the chairman, director, and everything okay. He said, oh, it's amazing, So I went to University of Florida 1 year, from 88 to 89. So I came back to Japan 89. Only I need 3 years to develop blue LEDs. Only using 3 LEDs, I could win Nobel Prize. This was very easy. But it's true story. Very easy. Because the first 10 years, very hard time. Because no background semiconductor technology. So just for blue LEDs, I change the material for gallium. I use the gallium aluminum arsenide. I change the material to this material, nitride material. And device processing and other character measurement, same, basically, same. So that's the reason. Also I change the epitaxial growth. For this one, I use liquid phase epitaxial growth. This one is MOCVD. So just change the material and the epitaxial growth method. And other devices, process and fabrication, characterization, very similar. So that's the reason I need only 3 years. Because first 10 years, I had everything, nothing, from the bulk crystal growth, substrate, everything. Everything, all equipment made homemade, Ooh. Oh, sorry. So first 10 years, first 10 years, I had to develop bulk crystal growth, gallium arsenide, gallium phosphide, bulk crystal growth, and I spent 3 years to develop this product. And I sold these crystals, also substrate. And after making substrate, we did the epitaxial growth for the blue, red, infrared, and red LEDs. These lines, reactors, everything, they're homemade, I told. So I could make this product, but the product is very poor. I told you, monthly sales, 10,000 US. But after invention of blue LEDs, company name value is skyrocketing, so these sales are now increasing dramatically, I heard. So this is just in 1995, newspaper reporter came to interview. So we had an interview with this is the founder of the Nobuoka and with me, just and so this is a liquid phase epitaxial growth. This is just I took a picture, not my reactor design, but basically, this is the crystal, this is not so liquid phase, not this is horizontal version. For bulk crystal growth, we use the horizontal Bridgman method for gallium arsenide, gallium phosphide. So I could make it, but using a homemade reactor, because this is we use the quartz tube. Inside it, vacuum sealed quartz tube. So this is very tough, especially for quartz welding. We use a hydrogen and oxygen burner to weld these quartz, And this is sometimes cracking happen, and after increasing temperature for the around 1,000 degrees, explosion happen. Every month I got the explosion. This explosion is so big, It's like a dynamite explosion, because for gallium phosphide we use phosphide, and the phosphide used for source material for the explosion material, And arsenide also, we had explosion. In this case, oxide arsenide is very toxic material, So you can see, so this quartz is a big one, This is a hard time, like this burner, So using, you had the welding and burner. And every month explosion, At that time, I thought my life is over, Because, my friend, of the university friend, Tokushima University friend, sometimes they called me, and I asked them, what are you doing? Yeah, we went to the international conference in Hawaii. We did a presentation about Nakamura. What are you doing? I couldn't tell them anything. Oh, I'm okay, because I was what doing that in the outside of a company. I was, repairing the explosion furnace. My God, no way, no. So every day, I was this welding, quartz welding, early morning to the night time because this is terrible time. Okay. So next, after making bulk crystal growth, bulk substrate, I did epitaxial growth. You can see this is my designed homemade epitaxial growth reactors. So what is an LEDs? So next is LEDs. So basically, basic structure of LED also laser diodes, very similar, just with substrate. Substrate is LED with sapphire. On sapphire substrate, we need 3 layers. One is N-type layer, and the next is active layer or emitting layer. And then finally, a P-type layer. Just we need 3 layers to make LED and laser diode. But in the case of blue LEDs, missing layer is this emitting layer and the P-type layer. N-type layers has been available from beginning. So just we had to develop 2 layers. So after developing 2 layers, we could demonstrate first high brightness blue LEDs in '92, basically '92. So basically, emitting layer, we use these materials, indium gallium nitride. By changing composition, we can make basically red to violet or UV LEDs. So commercially available LEDs is UV LED to green LED right now. But in the future, we have to develop red LEDs. Also, using aluminum gallium nitride, we can make UVC. UVC LED can be used to infect the COVID-19, all kind of virus and bacteria. So next is the impact application. So probably application is all kind of display and lighting, and now use LEDs because it's a solid lighting, so very reliable. So you probably So interesting is agriculture. Okay. So this shows the efficiency of the LED lighting. So now 300 mAh. So encompass conventional lighting. Very efficient. So encompass a light bulb. Almost more than 10 times efficient, and encompass fluorescent lamp 3 times efficient. So this shows all the data. This is DOE estimate, long time ago. I think, when maybe 15 years ago. So at that time, they estimate, in the United States, if the LED gradually replace the conventional lighting, by 2020, we can save energy amount of equivalent to the 19 nuclear plants, only in the United States. But all over the world, equivalent saving energy is equivalent to 60 nuclear power plants. But this is still adoption rate of LED is very small, like 10% adoption rate. But the latest one is just last week. My former student, Morgan Patterson, did a presentation at our university because he worked for DOE. Also, he's doing consulting of DOE. Still, he has a consulting company. So he showed me the latest DOE estimation of how much energy saved by using LEDs. So this is site energy consumption. So basically, you can see just here is easy. So annual energy saving in 2021 is about 25 billion dollars. 2021 is here. So only small portion, about I think 30% of the all of the among the lighting is replaced with LEDs. But the 2035, their estimation 75% of the lighting would be replaced by LEDs. So in that case, cumulative saving from 2070 to 2035 is $570 billion saved by changing the LED from here to here, this one. So it's a huge saving. Also, another interesting thing is, you can see, so this is U.S. electricity retail sales to major end-use sector, So basically, this is industrial usage of electricity in the United States. This is a commercial area, and the residential area is this green one, and transportation is small, like this. So interesting thing is here is usage of electricity saturated almost in the United States. No more increase, because many kinds of things contributed, this, usage is saturated. So it's very good, In 2010, 20, almost saturated. And this one is electricity usage per capita, So this is only residential electricity, residential electricity consumption per capita, So this one is, saturated around 2010, 2015, and they say, DOE says, while multiple factors contribute to the decline, I argue that the rapid emergence of the LED and other energy efficiency lighting has played a particularly important role. So basically, this shows the evidence of declining electricity used by U.S. household period. So basically, they say the LED saving collaboration. This one, basically, LED lighting reduces the usage of the residential electricity. So now it's saturated, So this contributes to saturation of all of the electric power consumption in the United States. So next is agriculture. So this is vertical farming, So this is because due to global warming, outside agriculture means agriculture is unpredictable. Weather is very strange. Also, future we have to leave the space. So space agriculture, we have to use this technology. Only choice lighting should be LED or laser lighting, And using this technology, no nighttime, so growth rate is 2 times higher because the plant has to grow 34 hours. And the yield of the plant growth, this one is much higher outside because weather is controlled, And the water is reusage. Water usage only 1% compared with outside. And they stack each other, so, they can reduce the cost. But still, still cost is high because, my former student says problem is power is still electric power is used a lot, so still cost is high. But the lettuce, in the case of lettuce, still lettuce is now almost okay. They can be profitable. So this is Newark, You can say, the world's largest and most productive vertical farm. So this lettuce growth is okay, he said, more profitable. But the other, vegetables still, he said he doesn't know. But another good one is more profitable is marijuana. Marijuana, they don't care of the price. So he's at Los Angeles. Marijuana is a high technology, he said, and the most profitable. So it's a lot of, there's marijuana horticulture lighting, So it's crazy, but I don't know. High technology is for those one, I don't know. But anyway, so this technology is very important for future because we expect the future, we expect a shortage of food. So in that case, due to global warming, so this is a controlled one. So also space agriculture. So next is solar powered LED lighting. So basically, all over the world, 1.5 billion people live without any electricity. These are countries, So it means they have no lighting, no access to lighting. So for lighting, they use the kerosene lamp, basically oil lamp. But the problem is the oil lamp is very expensive. Now recently also more skyrocketing, So now distance is much. This is older data, so now it's I think double, $300 per year. It's very expensive, and also it's called the fire and for health, not good, no. But now they use this one. This is older data, so LED, charge the solar cell and it's just operated battery charged solar cell. So today I enjoyed the lab tour, Conn Center. So they're developing the new solar cell, cheaper, new cell efficiency higher. Also they built a new battery. So in the future we have to use Conn Center as a solar cell and the battery. I said they are doing a great job. So basically, lifetime of solar cell and LEDs are like 20 or 30 years. So that's the reason this is much cheaper. But right now, battery lifetime is not so good. So that's in $3. If battery time becomes 20, 30 years, this one is almost zero, 0.1. So it's very cheap. That's the reason, this technology is very popular in South country. Because kerosene is like now $300 per year, very cheap. Okay, so next is I talk about how I could develop blue LEDs. So since 60s, many scientists tried to develop blue LEDs. So emission color is determined by materials. So blue LED, blue laser, two kinds of material available to develop blue and green LEDs, zinc selenide or gallium nitride. So this is a cross-sectional TM. Zinc selenide, you cannot see anything when grown gallium arsenide. So no defect, no crystal defect. Gallium nitride is usually grown sapphire. You can see dark line. This is a crystal defect. Number of crystal defects, 10 to the 9th. Still same crystal defect. You can see LED all over the world. Crystal defects like this, same. So at that time in 80s, 70s, they are common sense. To make LEDs, dislocated density less than 10 to the third, 10 to the third. This one is less than 10 to the third. This one 10 to the 9th, 6 order higher. So 80s, 70s, if people try gallium nitride, they are called crazy or foolish. It's true story. After invention of blue LED, I talked to the Sony scientists after conference, We went to dinner together. And the Sony scientist told me, Nakamura-san, you are lucky. Why? Because you work for a small company. You work alone, so you can make a decision of which material is good. Yeah, I selected gallium nitride myself. But Sony, they formed a project team. Like 10 science composed of the 10 science, 10 science is the project team, And at first they discussed the material, zinc selenide or gallium nitride. And 9 scientists is zinc selenide. Yeah, it's common sense. One scientist say, how about gallium nitride? And 9 scientists, you are foolish. What happened? What did you study in the solid state physics at university? Did you study physics? All of it, so she said, the dislocation is 10 to the third, 10 to the 9th, no way, 0. So that's the reason, if you have meeting, zinc selenide. So that's the reason all of companies select zinc selenide. If crazy guy alone, it's okay. I can select gallium nitride. So that's the reason, startup company is very important. Because startup company only few people, just make a crazy thing okay. But the big company, always meeting. In that case, all idea become common sense, no way. So basically I came back to Japan from University of Florida, 89. So I started blue LED selecting gallium nitride. So all scientists selected zinc selenide, 99%. To show this than Tesla. But gallium nitride on side, 10 to the 9th, only few groups all over the world, they work with gallium nitride. So in Japan, in this field, the biggest conference, the Japanese Society Applied Physics Conference, always number of attendees 5,000. So at first, the gallium nitride session, each speaker is 15 minutes talk, only 2 speakers, and 30 minutes, after 30 minutes, this session is over. And I went to the next zinc selenide session. Zinc selenide, the largest lecture hall, and more than 500 people there. People cannot enter. I couldn't enter the room. So at that time, zinc selenide people, gallium nitride now, here's gallium nitride, have to move zinc selenide somewhere, crazy, because the zinc cyanide, in 91, American company 3M developed the zinc cyanide-based blue-green laser diode. But laser diodes are technically more difficult than LEDs. So other than everything, zinc cyanide winner. So yeah, gallium nitride is a bad. But in my case, I went to University of Florida for 1 year, from 80 to 89. So initially, my purpose is, how to operate MOCVD. I wanted to learn how to operate MOCVD because the university, professor of University of Florida, you can come to University of Florida to learn how to operate MOCVD. So that's the reason I went there. But when I went there, no MOCVD system because the professor said, due to funding problem, my MOCVD was taken by other professors, so you cannot use it. But if you can construct the MOCVD, I have a part. You can construct the MOCVD, you can use it. So we spent 1 year to construct this MOCVD. I could operate one run, so during this construction, I had to work together with PhD students. And all PhD students asked me, Nakamura-san, do you have a PhD degree? So I said, no, I don't have a PhD degree. So about scientific paper, have you published any scientific paper? I said, no, 0. My age was 35 years old. Because a small company, it was forbidden to publish any paper, everything confidential. So, and 1 year later, I came back to Japan. My dream became getting a PhD degree. Because I understand United States PhD is very important, because without PhD degree, United States, people are not call you a scientist or researcher. Science researcher means we have need PhD degree. So there are two materials available, zinc cyanide or gallium nitride. So zinc cyanide, every year, I don't know, I never counted, maybe 100, 200 papers. But gallium nitride only 1 or 2 papers. So I selected gallium nitride because it's easy to publish paper. Because in Japan, at that time, we could get a PhD degree without going to university. Just publishing more than 4 or 5 scientific papers, we could get a PhD degree. It's called a paper degree. So that's the reason I wanted to publish a lot of paper. So that's the reason I selected zinc cyanide, because it's easy to publish paper. Because publishing paper is very easy, just do some experiment data and I did some physics or theory, you can publish paper, That is a paper, It's very easy. So, but I never expected to invent blue LEDs. Just after publishing 5 scientific papers, I want to say goodbye to the company, That is my story. But coincidentally, I could invent a blue LED. So basically, we need 2 layers. I told you, indium gallium nitride, p-type gallium nitride. So I had to develop these 2 layers. So initially, I purchased MOCVD. This is a reactor to grow gallium nitride. Because founder gave me $5 million. I purchased $2 million MOCVD from, and I tried to grow gallium nitride a couple of months, but no crystal growth, 0. Even the growth, black color of gallium nitride. The other color is transparent, no color. So I worked for a couple of months, no result. Then I started to modify the reactor. Every morning I modify the reactor, and every afternoon I did epitaxial growth round, maybe five rounds every afternoon. Every day I continue this pattern. Every morning modify the reactor. Afternoon I did experimental epitaxial growth round 5. And I continue this pattern 1.5 years without any Sunday, Saturday. I enjoyed only New Year's holiday, just a couple of days. Then 1.5 years later, I developed this MOCVD. I named 2-flow MOCVD. Just MOCVD is just 1 flow to get a laminar flow, but I added an additional flow, sub-flow. Everybody expects this is called a turbulence flow, but after adding this one, beautiful laminar flow. And after this invention, I could achieve the breakthrough in this field every couple of months. Every couple of months, best in the world. The epitaxial growth, crystal core is best in the world, LED is best in the world. Still, Nichia is a top company because they use this reactor. This is the most important breakthrough in my life because this reactor is best, any crystal is best in the world. So reactor design is very important in this field. So for p-type layer, so usually people dope the magnesium to get the p-type layer, but after doping magnesium into gallium nitride, always resistivity semi-insulated. But in my case, just do the summary annealing. We got the resistive p-type gallium nitride. Also, same time, I clarify the mechanism, why we got the p-type gallium nitride. Just hydrogen passivated the magnesium acceptors, and using summary annealing, we can remove the hydrogen. This is called the hydrogen passivation. This is a 30 years mystery, 30 or 40 years mystery. Nobody could solve this problem. I could solve this problem, this is physics. This is not important for company. Company is only interested in making a product, but just confident, secretly I work for this side wagon, side fighting, something. And the next is emitting layer, indium gallium nitride. So this is also very important. This layer emits the blue light, green light, all kinds of color. But the several groups tried to grow this material. Nobody could get the high quality, which shows blue emission, green emission at room temperature. Nobody. But in our case, using two-flow emissivity, we observe the first strong blue and violet emission. Because the two-flow emissivity is so good, any crystal growth best in the world. So after invention of two-flow emission, everything very easy. So in '92, we solved these two layers problem, and just we stuck to three layers, and we could demonstrate the high efficient blue LED in '92. And I showed the chairman, founder. Why don't you use the press release? With the press release, all of the people are surprised. He said, no. You have to do the mass production of blue LED. After you are starting a mass production of blue LED, you can do press release. Okay, it's okay. So it took another 1 year to prepare for mass production, because the company is only just making product, not physics at all. So 1 year later, we could start the mass production blue LED, and this is the first our blue LEDs, And the Nobel Prize Foundation also cited our first blue LEDs. Also next, in '95, also we developed the first blue laser diode or violet laser diode. This is a big thing, but nobody cares about. But initially, we expect that this blue laser is used for Blu-ray DVD. But the Blu-ray DVD market is very small due to internet, everything, internet. So, but now this blue laser is laser lighting, because so right now white LED is blue LED and coated phosphor. But laser lighting, the blue laser diode is coated by phosphor. And the advantage of blue laser diode, at the power is 100 times higher than the blue LED, 100 times. So 100 times brighter. So right now, this laser lighting is automobile headlamp, especially Audi and BMW, they use this laser lighting. The distance is now up to 1 kilometer. And the LED headlamp is only 300 meters, and all the traditional current one is only 100, 200 meters. So in the view of safety, much better. Also, laser lighting is a point light, ultimate point light source. So if you use this laser lighting for automobile headlamp, size of the headlamp is this size, like eye of the human eye. So you can see in your future. Also, laser lighting is a laser projector. Now all the projector is now using movie theater, or now use a laser projector. There is a high power blue laser diode, green and red, there is phosphor. So also, I asked this projector is the older one, they like to use the next one is a laser projector. So all movie theater is a laser projector now. And advantage of laser projector and laser headlamp is a point light source. So using MEMS mirror, it become a projector. So automobile headlamp becomes laser projector. So it means if a camera sensor detects that this car is coming, project any image. Okay, so this is dark. So this is a dynamic laser lighting. So it's coming soon. And so another application, wireless communication. So right now, Wi-Fi is the wireless communication. So wire is radio frequency due to regulation. So now 3G is this region, 4G, gradually frequency increase. And now 5G is the limit of the RF. So after 5G, 6G, no way increase the data transfer rate. But the blue laser diode, laser lighting is the frequency is 6 orders higher than the highest radio frequency. So bandwidth is almost infinite, and so this is a future wireless communication tool. Also, same time lighting. Also, another big thing is laser welding. So all the automatic laser welding cutting is used for everything, But right now, laser welding cutting, they use this, infrared laser, this region. But this is absorption coefficient, you can say. So all metal, gold, nickel, copper, silver, aluminum, absorption coefficient here is almost close to zero, But blue is very high. For metal welding, cutting, blue laser is best, So this is very important. So laser welding and also 3D printing. Now many companies now already use this blue laser diode. But also very important is I told this to people, right now Russia invaded Ukraine, and Ukraine tried to shoot down the missile, but the only few part of the missile they could shoot down, but a lot of missiles come to the Ukraine, a lot of people dying. But to shoot down the missile, we need laser gun. Laser gun is the ultimate weapon, People just scan the laser gun, we can shoot down the missile. So I think laser gun is very important now to get a peaceful world. And also we are working for the UVC LEDs because of coronavirus, COVID-19, because right now mercury lamp is used for disinfect all kinds of viruses and bacteria, but this is the traditional vacuum tube type lighting. But same as lighting, all the traditional lighting is replaced by LED lighting, So we are developing a UVC LED lighting to disinfect all kinds of viruses and bacteria. So UV means the UV-ABC, UV-ABC, many kind of application, water purification, air purification, sterilizer, also UV is many kind of application. But still not good because power is not good. So this is one example, COVID-19. So how UVC, but the UVC LED light, destroys the DNA. So for human, it causes cancer, It's not good. But this is one example. For 10 milliwatt UVC light, irradiate coin size, 1 second we could disinfect all COVID-19 virus. 1 second, 10 milliwatt. So we can make a 100 milliwatt LED UVC lighting, size becomes this size. 1 second we could disinfect all the virus. So we need the high power, UVC LEDs. So right now problem is cost. So mercury lamp is very efficient, 30 or 40%. Cost is only $2 per watt. But the UVC LEDs, commercial available is about 5%, and cost is $400 per watt. So that's the reason not so used for many places. It costs too high. This is a blue LED, white LED. White LED blue is very efficient, like 60, 70%. In that case, cost is $1 per watt. So our goal is we have to achieve the UVC LED efficiency about this level, 67%. Now UCSB we developed up to now 10%. Now 10%. So another 6 times increase, and it becomes $1 per watt. So in that case, this UVC LED is for everywhere because it's very cheap. Cost is very important. So listen to UCSB. So this is a big world population. So UCSB is now top 3, and these two guys are still top, but now increased dramatically. So So in the future, And now highest power is we achieved about 100 milliwatts. So 100 milliwatt, this size, 1 second, we could disinfect COVID-19. Because this is because we installed this one for the air conditioner inside the duct, we kill any kind of variant. Doesn't matter, any kind of variant. Because the vaccine, every time variant appears, new vaccine, endless, So, okay, so another application is new application, micro LED. So now you can see that this LED display, you can see baseball stadium, basket stadium, you can see large LED display. But in this case, chip size is 300 micron and 1 millimeter. But now, many IT companies develop the micro LED display. These chip size is micron size. In that case, these are LED used for this smartphone and AR, especially AR. They're interested in AR. So the advantage of micro LED is this one. This is OLED, LCD. Any categories, micro is the best. You can say for self-emission or the brightness, everything is best in comparison to display. So that's the reason all of IT company and the display company working on micro LED. But except one problem is cost. Cost is too high. So, but especially all of IT company, in the US, a lot huge IT company, Google, Apple, Computer, and Meta, Facebook, So they want to make this one AR, because right now smartphone is available, but the smartphone is only sit down. But this AR is a walking, you can check everything. So smartphone is developed Apple computer, but all of IT company, next one is this AR, they want to become camera. So I don't know what kind of software this is, but all of IT companies are display to develop this AR display using micro LED or big cell. Okay, that's all. Thanks so much. Bye.
You have questions?
Professor Nakamura,
Yeah.
impression when I walked in here that the green LEDs were invented before the blue LED. But one of your slides showed that the green was produced after the blue.
Yes.
Is that correct?
Yes, green is available since maybe green is available since 60 or 70, but very dim. Very dim, gallium phosphide, indirect, but very dim. I don't know. Only they can use, but the blue is so bright after invention. Blue LED almost equals green, 100 times brighter than green. So they cannot green. So, but after invention of green LED is 100 times brighter than older. So that's it. Because gallium phosphide, indirect material, it's very difficult to make efficient green. So.
Other question? Please use the mic.
First, thank you for the talk. It was very insightful. I enjoyed it a lot. Second, do you think that there's still room for improvement with the material that you made the blue LEDs with, or do you anticipate improvement in blue LEDs with another material?
Yeah, because the company says still, few percent increase is a big change in the market share, they say. So company is working on just increase further, but there's still a lot of space, because I told you, still water pollution is about 70, based on 78, still 20 or 30% increment is required. So yeah, still space. But the university, we are not so interested. University is we challenge a totally new technology. Yeah.
Hi, Kevin Walsh, Speed School here, Associate Dean of Research. First of all, thank you for quite an impressive talk. It was really, really inspirational. The fact that you could do some of those things that you did. I think we appreciated the story and the history as much as anything. It was amazing what you were able to do with, not all the great resources, available to you. And it's also really inspirational, just the impact that your work has had on society. You know, that's what we all strive to do, but all of us don't get there like you have. I was just wondering, just with the rest of your academic career here, what big challenges you plan to focus on for the, your next step here? Do you continue on making, I would say, incremental improvements here, or is there some other kind of really big challenge that you are interested in focusing on?
Yes, thank you so much. So I think at the university I do both. Big things or incremental improvement, both, because our funding source mainly from industries. So some industry needs some kind of increment, also both, no? So we are working for both. And big change is, we ask the student to work for the big thing, but it's a gambling. So sometimes great results, sometimes nothing, but gambling, but very important for big change thing, because the university, even if fail, it's okay, but it's working for both, at the university, yeah.
Mahendra, hang on.
So if you're looking for a big challenge, I mean, N-type doping in diamond has always been a challenge. PN junction in diamond could give you UVC, a better UVC than anything else. Is there any thought on that?
Any type, N-type, looks type, I don't know, I never worked with diamond, so yeah. Just for teaching, I studied diamond, as a next white bonding material. So I don't know. Just for good reason, but gallium P-type gallium nitride, because past 30, 40 years, many scientists worked to make a P-type gallium. Nobody could make it. Nobody understands. But it's a hydrogen passivation. It's simple, after understanding, So I think most important just experiment, to analyze the experimental data, using. Always I say, so yeah, I forgot to talk about one thing. So for first 10 years at Nichiya, I read all kinds of scientific paper and patent, and then I did experiment. Those experimental is very unintentional. I copied their technique. So when I started blue LEDs, I didn't read any scientific paper, patent, zero. Just I worked to experiment, and the experiment data, I analyze the experiment, and next growth run. And then I clarified the P-type mechanism. I didn't see any scientific paper. And looks like hydrogen is related, And I read in the scientific paper, many scientific hydrogen passivation papers available among 3-5 and silicon. So I think most important, focus the experimental results. In this case, your own idea means the creative idea. If you read a scientific paper, unintentional copy, it's not a creative idea. So just focus the experiment and using your idea, and it's a creative idea.
So you kind of hinted at in your story, talking with the engineer from Sony, that because he was working for a larger research institution and larger research teams, that they didn't have the freedom to kind of work with materials that, individual scientists would, bring up to meetings, they would get shot down. So do you think there is a proper middle ground for research institutions to shoot for, whereas we still want, collaborative groups to exchange diverse ideas, but we still like to have the freedom to incorporate new materials? Do you kind of see a shift in research institutions going towards a mix of both, or do you think it's still going to grow to be bigger, larger? Do you have any thoughts on that?
I think big institution always we have a meeting, We should have a meeting, and if we have a meeting, there's a meeting guy, very big voice guy, and they automatically determine what he said or she said. I think I don't like meeting for research. because meeting is always conclusion is common sense. Because always each person says, oh, I studied physics theory, so he wants to show that his theory is something, but the crazy idea is it's coming from the individual. So that's the reason, start companies very important. United States start companies make a very good product, software, IT company, because start company is small number of people. In Japan, Korea is always big company, no start company. So because always try the common sense research, I think startup companies are like individual, small group, so they can try crazy ideas. So that's the reason American economy is so good due to startup company. So I think startup company shows that individuality, crazy idea is most important. But the meeting, big company meeting, big companies, how many meetings, that is bad, Crazy idea, dangerous, possibility very small, but sometimes work,
Any other questions? Yes.
Hi, this is Riyadh from physics. You mentioned about blue lasers, right?
Yeah.
So can you give us a little bit detail of that? Are you using a cavity to create the laser? How the laser was created?
What laser, what is?
The blue laser?
Yeah, blue laser, blue laser is, so we started a company name is SLD, about, hold on, 10 years ago, to make a blue laser diode. And this SLD is commercializing this laser lighting and hyper blue laser diode. I think you can buy it. Now this company acquired by Kyocera, so now Kyocera SLD. And I think all over the world, only 2 companies selling hyper blue laser. My former company, Nichia, and my co-founded solar laser diode. So only 2 companies. So you can buy it and high power, and using fiber, we can make the connect all of this using fiber. We can make very high power laser diodes for laser welding, cutting. Of course, laser gun maybe, yeah.
Anyone else? Yeah.
Hello. Very, very nice talk. It was inspirational. Very, very inspirational. I was just wondering if you had any words of advice or encouragement for these young engineers and scientists trying to make even a fraction of an impact as you have in the science world.
Yeah, I think for young science, most important you need a basic knowledge of the science, So at first, you have to study at high school, university to get the basic knowledge, and also even at the company. But after you are confident of the basic knowledge, you have to challenge gambling. Research is same as gambling. Take a good word is take a risk, because gambling is success possibility almost of less than 1%. But if hit, it's like this, a big risk, It's the same thing as a company. If you work for a big company, salary is stable, but the salary is always small forever. But startup company, you join the startup company. In Silicon Valley startup company, success rate is 10%, 90% fail. But to succeed, you can get the big money, So all of Silicon Valley rich people, all rich people in the United States, through the startup company, they do gambling. If big company, no gambling, stable, but salary is always forever small. But the gambling means the startup company success rate 10%, and all rich people come from the startup company. So I think research same. You have to do gambling. Without gambling, without gambling, everything goes this way. You're very stable like a big company. But you gamble only way this way, very success rate very small, but the same as the startup company, success, big risk,
Last question. Anybody want to take it? Well, crazy ideas come from individuals. Gamble, take risks. These are great things to take away from our talk today. So everyone, please give a big hand to Dr. Nakamura.
Thank you. Thank you.
So we're having a casual get-together at Amelia Place at 2515 Longest Avenue. That's the President's House on Wednesday night from 6 to 8. Everybody's invited. And then tomorrow at the University Club from 9:30 until 2 is a poster session, energy showcase. Hopefully you all have posters in that. We're looking forward to seeing everybody there. There's lunch that will be served, so please take a break, come see the posters if you're not presenting. And everyone have a great rest of your day. Thanks a lot.